Well, welcome back to our next lesson. This is Mrs. Hanson. We're going to be picking up with section 4 of chapter 11, drawing organic molecules. And in this section, we see a variety of ways to represent molecular structures of carbon-containing compounds. So we're about 3/4 of the way down on page 9, just so you can see that on your notepad page. We can see a 5-carbon molecule. 1, 2, 3, 4, 5. We're learning is a functional group known as an alkane family, all single bonds in that hydrocarbon chain. And we'll learn that the prefix 5 will represent pentane. All 5 carbons, of course, in a straight chain. This is what we refer to as a complete structure of the molecule. Underneath that section, you're just writing in the complete structure of pentane. Knowing that from our last section, each one of these carbons is bonded to 4 different atoms, we can see that 4 bonded atoms on each of those carbons represents tetrahedral molecular geometry. And tetrahedral, of course, gives us those bond angles of about 109 degrees. So even though we call this a straight chain because it's not cyclic, it's straight, it is not really a linear molecule at all. We understand that the bond angles are 109 degrees. And so when we look at that, we have this zigzag as really the true molecular shape of that compound. So when we refer to a ball and stick model, the carbons are represented with a black molecular atom here, and the hydrogens are going to be represented with white as their atom. And we can see that the first carbon, number 1, had 3 hydrogens attached, but the bond angles, again, not the 90 degrees that the straight chain formula would have us look at, but more of a ball and stick model where it's zigzag, up, down, up, down. We then refer to a condensed structure where we eliminate all of those single bonds within that hydrocarbon backbone and just simply write CH3 representing the first carbon, CH2 representing the next carbon. Here's the next CH2. We have another group of CH2, and finally the terminal CH3 group representing this CH3 here. So a condensed structure allows us to put the hydrogen directly connected to the carbon. And then we see what's called a skeletal structure, in which we just simply show the carbon in a backbone zigzag format. So these are the types of structures we're going to practice in this section one at a time. In our first practice session, we're going to look at what we refer to as condensed structures. All of the atoms are drawn in, but the 2 electron bond lines and lone pairs on the heteroatoms are generally omitted. So as we looked at, for example, 1, 2, 3, 4 carbon chain, we're learning that this will be called butane, a 4-carbon alkane. And again, just as a reminder, as we approach this part of the lesson coming up, alkanes are just a family of hydrocarbons that contain all single bonds. We can shorten this condensed structure by moving from all these single bonds being shown to show connectivity to hydrogens and just show CH3. Here's that group. Here's the next CH2. Here's the next CH2 and the terminal CH3 written at the end. So a carbon that's bonded to 3 hydrogens becomes CH3 in our condensed structure, and a carbon that's bonded to 2 hydrogens simply becomes CH2. The bond lines can be drawn in for effect or to show specific bonding. So for instance, notice that 1, 2, 3, 4 carbon chain, but now on carbon 2, we have a branch coming up out of carbon 2 containing yet another CH3 group. I would call this the carbon backbone. It is the longest carbon chain, and it will be used when we go to name those compounds. So 4 carbons is the longest carbon chain, and often carbon 2 is another methyl group. And again, these words might be familiar, they might be brand new, but the term methyl means that it's a one carbon substituent branch, the CH3 group. And so we're just going to let that single bond remain so you can then see where it's coming out of the backbone chain. We can see that a carbon bonded to one hydrogen simply becomes CH as we move through that sheet as well. So if we wanted to just practice writing across from left to right, we have 1, 2, 3, 4 carbons in that chain. All of these carbons then are represented by the color coding. We can see the terminal CH3. Here's a CH2. Here's a next CH2, and finally a CH3. And in that last example that's color-coded as well, we had a CH3 that's color-coded blue. We had a CH color-coded green. Coming out of that is yet another methyl group, color-coded blue up here. Then we have a CH2, CH3 to complete the condensed structure. So this is a little bit of a time saver from having to draw in all the single bonds, understanding that every carbon has to be tetravalent. When we draw organic molecules, oops, I want to get rid of that. There we go, thank you. The identical groups can be condensed even further. And so looking at this example, notice color-coded in red in this 4-carbon chain, we have two groups in a row directly next to each other that are identical. They're CH2, CH2. So this particular part of the molecule can be further condensed by placing the CH2 group inside of the parenthesis with the subscript outside. And that's going to be read as taken twice. CH3, CH2 taken twice, CH3. But notice they have to be directly next to each other in order to simplify. In other words, we are not allowed to simplify elements or these little CH3 groups at the end because they're not directly next to each other. It wouldn't make any sense to be able to do that. So to simplify, what we're looking at is making sure that we notice they're directly next to each other, attached to one another. Now look at this example. In this compound, I'll color code this carbon yellow so we can see that it's color coded yellow as well over here. That particular carbon has two identical groups attached to it. In one direction, it has a methyl group, CH3, and in the other direction, it has the same exact group attached to it. So notice, I can place that group and read that CH3 taken twice. That tells me that there are two groups of methyl, CH3, on this color-coded yellow hydrogen. CH2, CH3 completes that structure because there are no similar hydrocarbon right next door to one another. So if I see a CH3 taken twice directly onto a next carbon, think about how that would represent two methyl groups attached to that original carbon. Let's try one. It says, let's practice converting each compound into a condensed structure. I have a letter A, and I think you have to flip. Let's practice. Well, this one I think I will need to put in a new page. So let's convert, and we have a compound, and I'm drawing what's on your page 10 at the very bottom. I just think I missed putting it in my PowerPoint. So I have 1, 2, 3, 4, 5 carbons in that straight chain. And it looks like at carbon 2, I have a CH3 again. And at carbon 4, I have a CH3 again. So I have CH3, the first carbon. I have 1 hydrogen coming up, and then 3 hydrogens coming off here, completing a CH2, CH, CH3, CH3. Now, I've just taken that time to show that I just wanted to match what that example is that says, let's practice. So what we need to do is write a condensed formula. And just to make things easier, I'm going to number those carbons in the backbone. So I can see 5 carbons in the backbone. Now, let's bring our attention to carbon number 2. Carbon number 2, as I examine it, has 2 identical groups coming off of it. Do you notice carbon number 2 has a CH3 coming off to the left and a CH3 coming down to the right? Those are identical groups, and therefore we can simplify by writing CH3 taken twice attached to the CH group. That CH group I'm referring to, I'll color code, how about in light blue? That's this CH group here. I'm going to color code these just so we can see where we've got. The CH3 taken twice represents what I've highlighted in pink, and the CH represents what I've highlighted in blue. We're now ready to go on to carbon 3, and in carbon 3, it looks like we have simply a CH2 and nothing really else attached to it. So let me color code that for us so we can see. I'm just color coding that. Oops, that was a crayon. We want a highlighter. I'm going to highlight that also in, let's say, gray. That's the CH2 group right here. Then what do we see? In the next part of carbon 4, notice carbon 4 has something else unique going on. And let's kind of find a color to represent. How about bright green? How about this kind of green here? Carbon 4 also has CH3 groups coming off of it. And so when I go to highlight that, this carbon that I called number 4 has also a couple of CH3s coming off. So carbon 4 is CH, and then coming off of it is a CH3 group taken twice. So we've written the condensed formula for that particular compound. Now we're ready to kind of practice some on our own. On the top of page 11, there's the letter B. You might have had that one written there as well. This is what we just did. This was the letter A that I hand wrote in. This is the letter B. So this was on the bottom of page 10. This is on the top of page 11. So we've already accomplished A. Let's do B together, and then I'm going to ask you to do those other practices and come back to check. So I like to number. We have 1, 2, 3 carbons in a row. And then I see an oxygen, and I'll call this carbon 4, just so we can highlight where we're at. In carbon number 1, I have a CH3 group, and I see nothing else attached to it. Carbon goes directly to another carbon. But now I'm recognizing that there's 2 similar groups of CH2, so I'm going to condense those and take them twice. Then I see an oxygen, and then I see a CH taken twice, Cl. Here's the CH2 and Cl all in a row for that last carbon. So the condensed structure for letter B would be CH3, CH2 taken twice, O, CH2, Cl. And remember, we're allowed to omit the electron dots on any hetero atom as well. Now you can do these additional practices. And when you're ready, come back and check on those with the video note. So pause the video and come back to check. Well, you're back, so you must be ready to check on page 11 your additional practices. We're just writing out the condensed formula. I'm going to just number to make sure we have the same number of carbons in our final answer. The first carbon, called carbon 1, is condensed to be written as CH3. I then see a series of CH2s in a row. I have 1, 2, 3 groups of CH3, 3 groups of CH2. So I write that CH2, and remember how we read this, taken 3 times. And then the terminal hydrocarbon is written as CH3. In letter B, I have a Br attached to a CH2, attached to a CH2, attached to a Br. Now, can those be condensed further? And the idea is they are not the same, because this first, if we did, it would look like CH2. I'm not even sure how to do this because we're not allowed. CH2Br taken twice might be the other option to write that, but it does not give us a clear indication of connectivity, so I would not encourage you to write it this way. Br, CH2 taken twice, Br would be another opportunity to condense that further. And that actually might be okay to do, because now I'm noticing that the Br can be attached to the first carbon and this Br is attached to the second carbon. But I'll tell you, this is probably the most common way you would see that written out. And let's try the last one. We have a CH3 group, then a CH2 group. We have an oxygen. I'm noticing directly in a row 2 identical groups, so CH2 taken twice, followed by OH. And a letter D. 1, 2, 3, 4 carbons in that backbone. The first carbon is a CH3. I notice that's 3 hydrogens on that carbon. Carbon number 2 is a CH2 group. Carbon number 3, that has a carbon, but it's also attached to all other carbons, so there's no hydrogens on it. But I do notice that the 3 attachments are all identical, that I've got 1, 2, 3 identical groups attached to carbon 3. They're all CH3 groups. So we would write that as CH3 taken 3 times. How are you doing? How about if we practice converting condensed structures to complete structures with all lone pairs on the heteroatoms? So it's just really going the opposite way. So I'm noticing in this first example, CH3 taken 3 times on a carbon that has no hydrogens attached. I understand every carbon has to have 4 bonds. 3 of those bonds are coming from methyl groups. Now it says write from each condensed, write the complete structure. So what I've just done was to simplify and just show an attachment, but I'm going to erase because I want to follow directions specifically and not take any shortcuts. And I'm going to show every single bond, even if they are to hydrogens, just to remind ourselves that every carbon has 4 bonds. And that way we've not taken any shortcuts. So 3 methyl groups onto this carbon, and that's what we have so far. That carbon then is attached to a CH2 group, so I know that that carbon with its 4 bonds is leading out to 2 hydrogens, and the 4th leading out to a nitrogen who's attached to a couple of hydrogens, and of course we understand nitrogen would require its lone pair. So there's the complete structure with all the lone pairs on the heteroatom of nitrogen. Letter B, I notice that I have a methyl group, so I have a CH3. That carbon has to have 4 bonds. 3 of them lead to hydrogen. The 4th leads to the next carbon. I see that there's 2 hydrogens on that carbon, and it's leading to a next atom of oxygen. The oxygen is going to require 2 sets of lone pair electrons to complete its octet. The next carbon leading out after the oxygen has a single hydrogen on it, and it has 2 groups of methyl. CH3 taken twice shows 2 groups of methyl to complete the octet on that last carbon. And when we compare those, that's exactly what we've modeled. If you'd like to take a moment and pause the video and check our work against what we wrote, we have a match. When we draw skeletal structures, we assume that there is a carbon atom at the junction of any 2 lines or at the end of any line. A skeletal structure, for instance, are these zigzag lines. At the terminal end, we know our carbons, and at every junction of any 2 lines are also carbon. So when I draw that zigzag line, I actually just showed you a 6-carbon chain. We assume that there are enough hydrogens to complete every carbon's requirement of having 4 bonds. And we do need to draw in all heteroatoms and the hydrogens that are directly attached to them. So let's suppose I had an OH. I'd have to draw in the oxygen and its hydrogen. And so as I look to practice drawing skeletal structures, they can be straight chain or they can be cyclic. Wherever I have a carbon, we have a junction of 2 lines. Carbon 1, carbon 2, carbon 3, 4, 5, 6. I eliminate all those single bonds to the hydrogens, and we've drawn a complete structure of cyclohexane, and we've drawn a skeletal structure of cyclohexane, eliminating all of those single bonds to hydrogen. If I have a cyclic structure that has a functional group, we show that functional group. We are not allowed to eliminate that. So here I have a cyclopentane, and it has an alcohol functional group. The OH is the alcohol functional group. Notice how it's ending in ol. So this functional group is represented, I'm just going to call that right here, that same carbon. So I have a cyclopentane. Notice that I have a 5-membered ring. Looks like a little house when I draw it. And the OH group has been drawn in skeletal structure to show the alcohol at that position in the cyclic structure. These are a great deal of time savers, aren't they? So now we're up to top of page 13. We're asked to convert each skeleton structure to a complete structure with all hydrogens and carbons drawn in. So at the junction of every carbon line bond, we know that this is a carbon, this is a carbon. Every line segment joining represents a carbon. Every carbon must have 4 bonds, showing that carbon needs 2 hydrogens on each of these cyclic structures. And in letter B, we understand that every line junction is a carbon. So here we have a cyclopropane. One of them is leading out to a chlorine. Every carbon must have 4 bonds, leaving 2 bonds going to hydrogens. 1 hydrogen to complete that carbon. And then don't forget, any halogen needs 3 sets of dots to complete its octet. And that's exactly what we've shown. We remembered to add hydrogens to each carbon at the junction. And we remembered to add the lone pairs of electrons to the halogen of chlorine. Let's keep practicing. Convert each skeleton into a complete structure with all C's and H's and lone pair electrons. Feel free to pause me, work ahead. That really does help. Don't cheat yourself. Make sure that you're practicing as we work together. If you come back to the video when ready, and let's check. Letter A, I'm counting 8 carbons in that cyclic structure. So between carbon 1 and 2, here's 3, 4, 5, 6, 7, 8. And that's as best I can do to come out that same way. Every carbon needs to have 2 hydrogens attached. So all that was necessary to complete this cyclooctane compound was to add hydrogens to each of those carbons to create a tetravalent carbon. So I'm just adding 2 hydrogens to complete the octets. Easy enough. Here we have 1, 2, 3, 4, 5, 6 carbons in a cyclic structure. So 1, 2, 3, 4, 5, 6. Oh, good, that one came out a little bit better. Now, every carbon requires 4 bonds. One of the bonds goes to chlorine, therefore we know the other bond has to be a hydrogen. And also, we've got to put on those electrons onto those chlorines to complete its octet. And that's going to get redundant for each one of these. We're going to add on each set of dots to the chlorine and make the 4th bond go to a hydrogen. And we'll do that for all 6 carbons that are in this cyclohexane compound. And one more. Got it. And how about the letter C? We have 1, 2, 3, 4, 5, 6 carbons. So let me get that cyclic structure set up. Each carbon requires 4 bonds. Let's call this carbon 1, 2, 3, 4, 5, 6. Carbon 1 has an alcohol group, so I know that has an O bonded to an H. The oxygen requires 2 sets of electrons. The 4th bond coming out is a hydrogen. We don't see it, but we know it's there. Carbon 2 has a nitrogen, and it's leading out to 2 hydrogens, and it also requires a set of electrons, and the hydrogen completes that carbon's octet. Carbon 3 has 2 hydrogens. Carbon 4 has 2 hydrogens. Carbon 5 leads out to a methyl, which has 3 hydrogens attached to the carbon. And this carbon needs a 4th bond as well, so there's its hydrogen. And then carbon 5 would have its 2 hydrogen bonds. So you can see these line structures are indeed a great big time saver. Carbon chains are also drawn with skeletal structures using the same principle, and we looked at that as drawing them in a zigzag fashion. So even though we're calling them straight chains, they are far from straight. In other words, knowing that the tetrahedral shape, the 109.5, gives this shape actually some molecular geometry of a zigzag line. 1, 2, 3, 4, 5, 6 carbons. And we can see that as 1, 2, 3, 4, 5, 6 carbons in its skeletal structure. Notice we are eliminating any type of bonds to the hydrogen because we know they're there. As an example, on the top of page 14, it asks us to draw on all the carbon atoms, the hydrogen atoms, and lone pairs that we would find in the following molecule. So I'm going to number 1, 2, 3, 4, there's a double bond, 5, 6, and that carbon number 6 has an OH leading out to it. So we would have 1, 2, 3, 4, 5, 6 carbons in a chain. Carbon number 2 has a double bond leading up to it. Between carbon 3 and 4 is a double bond between the 2 carbons, just to keep track. And carbon number 6 has an OH leading out to it. I better show the bond, O to H. Now let's take care of the hydrogens and the lone pairs of electrons. Carbon 1 requires 4 bonds, so I better fill in 3 hydrogens to satisfy its octet. Carbon 2 already has 4 bonds, 2 of them are leading up to the oxygen, and 2 are in the straight chain of the carbon backbone. Don't forget the oxygens, lone pair of electrons. Carbon 3 has 1, 2, 3 bonds. It needs a 4th hydrogen. Carbon 4 will require a 4th bond to a hydrogen. Carbon 5 requires 2 hydrogens, as carbon 6 does as well. And then don't forget the lone sets of dots on the oxygen to complete its octet. A few more to practice there, and we can go through and kind of show how we did that. So we took all those carbon atoms step by step and turned it into a zigzagged line structure with all of the electron dots shown. And this is the exact final answer that we wrote on the previous page. But notice how we have the molecular geometry presented as well. Carbon 1, 2, 3, 4, 5, 6. At carbon 1, that was a tetrahedral, so we know that the bond angles would be 109. Carbon number 2, well, that has 3 electron domains, 3 atoms that are bonded to it, so that would be called trigonal planar. And trigonal planar has a molecular geometry just like an equilateral triangle, 120 degrees. Carbon 3 has the same geometry. It has 3 bonded atoms. That's trigonal planar. Carbon 4 has 3 bonded atoms. That's trigonal planar. Carbon 5 is tetrahedral. So carbon 5 is like carbon 1 with 4 bonds. As is carbon 6. Carbon 6 has 4 atoms bonded to it, and it would also be tetrahedral. Notice the oxygen, the OH, when we remember that O is also bonded to the hydrogen and the carbon it's coming from, this has 2 bonded atoms, 2 lone pairs, so this is referred to as bent molecular geometry. Let's try converting each skeletal structure to a complete structure, adding lone pairs on heteroatoms. So I recommend just starting by counting how many carbons do you have in this structure. Carbon 1 leads to carbon 2, 3, 4, 5, 6. When we complete the octet of each of these carbons, I got to put the carbon here up on carbon 2 as well. We're just going to add enough hydrogens to complete the 4 bond requirement on each of these carbons. So I'm just making sure that each carbon is bonded to has 4 bonds, and when doing so, that tells me how many hydrogens to add to each. So this is our answer to the complete structure from the skeleton from compound A. Let's call this carbon 1, 2, 3, 4, 5, and part of this ring structure is an oxygen as well. So for letter B, I'm going to start here, lead up to an oxygen, over to a carbon, down to a carbon, and kind of create that ring just as it appears in the structure. I can see that it comes down to a carbon, that's this carbon here, and then up to an OH. I'm going to just remember to complete the dot requirements on the oxygens. They both need 2 sets of dots. Perhaps it would be better to draw the dots opposite sides so we can see that there's 2 sets. And now I just want to make sure that every carbon has 4 bonds, and I'll do so by adding in enough hydrogens to do so. This carbon has 3 already, so it needs just 1 more. And every one of these would require 2 bonds to complete its octet. And that completes letter B's complete structure. Letter C. There are 6 carbons in that long backbone chain. So I'm going to just create a carbon chain that is 6 carbon long. 1, 2, 3, 4, 5, 6. Off of carbon 6 comes a bromine. And I'll remember to place its dots. What else do we have? We have a double bond between carbon 2 and 3, and we have a methyl group coming off of carbon 2. So now every one of these carbons needs 4 bonds, and I simply add in enough hydrogens to finish their octet. This carbon already has 4 bonds, so no hydrogen needed. Carbon number 3 needs 1 hydrogen to complete its 4 required. Here's carbon 5 and carbon 6. Easy enough. We move to the top of page 15 as we continue our practices. How many hydrogen atoms are bonded to each of the indicated carbon atoms? So here is our first carbon atom. I'll just highlight with the blue dot. I can see that carbon is attached with 3 bonds. So this carbon would need 1 more hydrogen. So it would have 1 hydrogen required. Carbon 2, let me just put a dot where it's pointing at. Carbon 2 has 1, 2, 3 bonds already. So it would require 1 more hydrogen. 1 hydrogen. Same answer for carbon 4. It's different. 1, 2, 3, 4 bonds already for carbon 4, so 0 hydrogens. It has 4 bonds already. But I missed this guy. 1, 2, 3 required, so 3 hydrogens on the letter for C, carbon 3. In the next, this is a molecule of fentanyl versus ibuprofen. This carbon, I'll highlight with a dot, has 2 bonds already, so it's going to require 2 hydrogens. This carbon here is attached to 2 other atoms, so it's going to require 2 hydrogens to complete its octet. The terminal carbon at the end of this chain requires 3 more bonds, so this will require 3 hydrogens. Carbon 7 has 3 bonds already, so it will require 1 more hydrogen. And I think we've got them all answered. So good work with practicing skeletal structures and condensed structures. I'd also like to talk next about functional groups in our lesson together. Section 5 carries on with the heart of our chapters really. In the preceding lessons, we take one functional group and study it one at a time. A functional group is an atom or a group of atoms with characteristic chemical and physical properties. A functional group contains a heteroatom, something other than carbon or hydrogen, a multiple bond, meaning double or triples, or sometimes it will have both involved. When we look at a functional group, it has components to it. We use the letter R to represent the carbon backbone. We then see a line between the carbon backbone and the functional group to just simply represent the covalent bond. And a functional group will be written after that in an abbreviated form. So the letter R is used to abbreviate the carbon and hydrogen portion of the molecule. This, for example, would be the carbon backbone of this compound. Since the compound is composed of 2 carbons, both of them are single bonded, we see the prefix eth to represent 2, and we'll know it's an ane suffix to represent all single bonds. And this then is the functional group we're learning is called the alcohol functional group, the hydroxyl OH. So here we have a molecule of ethanol. Hydrocarbons are compounds that contain only carbon and hydrogen. Now, they come in a variety of features, and it all depends upon the bonding within the carbon backbone. As I've said these terms before, The term alkane represents compounds that have only single bonds between all of their carbons. They have no other functional group. They're quite boring molecules, really. Hydrocarbons with all straight chains, no other atoms. Alkenes have a double bond somewhere in their backbone. And an alkyne, Y-N-E, alkyne, has a carbon-to-carbon triple bond as their functional group. As we learn naming in the chapters that are coming, you'll notice that an A-N-E suffix represents the family of an alkane. If we're naming an alkene, we use the suffix E-N-E. And if we're naming an alkyne, we use the suffix Y-N-E to indicate that there's a triple bond. And the fourth type of hydrocarbon functional group is a very special type of family, a ringed structure known as an aromatic compound. And an aromatic compound, just as you might imagine, has distinct odors as part of their physical qualities. The key here is that it contains a benzene ring, which is a 6-membered ring with alternating double and single bonds. Double, single, all the way around that ring. That is called an aromatic benzene ring. So we've introduced alkanes, alkenes, alkynes, and aromatic compounds. An aromatic hydrocarbon contains a 6-membered ring with alternating double single bond known as benzene. This is a chart that just allows us to kind of put in all of that fashion in just kind of an easy to look at kind of learning mode. Table 11.2, we have the type of compound known as an alkane, alkene, alkyne, or aromatic. This is what I'm asking you to fill in the left column. So on that top of your page, an alkane would have a structure there of RH, right? Then you'd see the alkene has the double bond. An alkyne has a triple bond. So this is what we're writing. I should probably highlight, otherwise we can't see it. We have an alkane, alkene, alkyne, and aromatic compound define the 3 terms next to the general structure. And it is our job to kind of work to memorize these types of functional groups. Here is a list of functional groups that contain a single bond to some sort of heteroatom. Remember, a heteroatom is an atom other than a carbon or a hydrogen. The first, and again, this is what you're going to write in on the left margin, are these terms here. So I want you to write those terms. We have an alkyl halide, and the alkyl halide has a general structure of Rx. Remember that X represents any halogen. So fluorine, chlorine, bromine, and iodine would be referred to as an alkyl halide. Here's a for example. Let's suppose I had a carbon, attached to a carbon, attached to a chlorine, and all of those, of course, would have hydrogens attached. This would be referred to as an alkyl halide. The functional group that contains the OH is referred to as an alcohol. A hydroxyl group is attached as its functional group. We need to know that as an alcohol. Here we have an ether. Now, an ether has the oxygen as part of the backbone of the hydrocarbon structure. So notice that the oxygen is attached to 2 other carbons. In an alcohol, the oxygen is attached to just 1 other carbon and a hydrogen. So that's very critical that we see that it's ROR. Here is an amine. The amine group has the nitrogen as part of its functional group, NH2. And the last one we're learning is called a thiol, and the thiol, you'll notice, has the sulfur as part of its functional group. Sulfur and oxygen have so much in common, as you might predict just based on where they live on the periodic table. Oxygen lives in group 6A, so we see that it formed 2 bonds with 2 sets of lone pairs. Well, sulfur lives right directly underneath oxygen on the periodic table, so it also has 2 sets of dots and 2 bonds. If one of the bonds is to a carbon chain and the other is to a hydrogen, we call this a thiol. If the oxygen is attached to a carbon chain and a hydrogen, we called it an alcohol. So we have a hydroxyl group, an alcohol, and then we have a thiol group with the sulfur hydrogen ending. Yes, we have to memorize these functional groups. When I say that, the skill level is trying to recognize what functional groups are present in an atom. Some examples. Here I have a molecule called di, meaning 2, ethyl, meaning 2 carbon chain, and the term ether represents that an oxygen is in the backbone. So then I read this, I can see that on either side of the oxygen, we have ethyl groups, a 2 carbon chain. This is an ROR, diethyl ether. Here's another example of an oxygen attached to 2 other carbons. It's an example of an ether. Let's keep practicing. Identify the functional groups of each compound, top of page 17. Here I notice I have an OH group, and I need to remember that's called an alcohol functional group. I have a straight chain carbon with all single bonds. This is what we refer to as an alkane family. Letter B, I see an aromatic ring. Notice that it's a 6-membered ring. So that functional group is an aromatic benzene ring. I also see that I have C double bond C, and that's that functional group that we called an alkene. Down here, I see a nitrogen group. We recognize that as an amine. I also recognize the same functional group down here as an amine, and this is all just straight chain carbon with no double or triples, so that's your alkane carbon backbone. Let's keep practicing. I notice in this example, an OH group is what we refer to as an alcohol. Here I'm noticing a C double bonded to a C in 2 positions. So this is the functional group we're learning as called an alkene. How about letter B? Letter B, I'm noticing is just loaded with halogens, right? So that fluorine, every time I see a fluorine, that functional group is what we refer to as an alkyl halide. I also notice that this oxygen group is in a carbon backbone bonded to 2 other carbons. This is what we refer to as an ether. And the last one on this page, I have a nitrogen that's attached to 3 other carbon. This is what we'll learn is called an amine, a tertiary amine. It's attached to 3 other carbons. It's the only functional group I see in that letter C. The functional groups continue with a carbonyl group. These are compounds containing a C double bonded to an oxygen. A carbonyl group is a C double bonded to an oxygen. Therefore, you can see that this is a carbon bonded to 3 other atoms, so it is called trigonal planar in terms of its molecular geometry. In a line structure, The C double bond O creates bond angles of 120 degrees. So carbonyl groups have carbons that are containing C double bond O. And there's quite a few that we need to examine and commit to memory. Let's examine those together. This is what I'm asking you to write in the left margin. In the first example, the first row, we have what's called an aldehyde. The aldehyde has a C double bond O at the terminal end of a chain, so that the carbon attached to the double bonded oxygen is also attached to a hydrogen. So a good note there, it says it must be at the terminal end of your carbon chain. If you see the carbonyl carbon, the C double bond O, within the carbon chain, we have what's called a ketone. So we'd have, in terms of carbon attached to two other carbon, instead of being at the terminal end, it's within the carbon chain. And that's what we called as a ketone. A carboxylic acid has the carbonyl carbon bonded to an OH group at the terminal end of a chain, a COOH. You'll often hear that written as COO, a COOH, where we have a carbon double bonded to an oxygen, that's the carbonyl definition, and it turns it into an acid with the OH at the end. This, we'll learn, is an acidic proton. Here we have an ester. An ester is a derivative of a carboxylic acid. Instead of having the COOH group at the terminal end, it's within the compound. So instead of OH, we have OR, where we have the compound is within. So we have C double bonded O, and then O, and then another carbon chain. So keep in mind, this is at the end of the carbon, at the terminal end, COO. And if it's not at the terminal end but buried within, we're calling it an ester. And the last is very special to nitrogen. If the carbonyl carbon is attached to a nitrogen, we call it an amide. So we've learned aldehyde, ketone, carboxylic acid, ester, and amide. And friends, what we're really doing is kind of laying out the chapters ahead of us in our course. Each one of these organic families will be studied in depth, one chapter at a time. It's our goal in this chapter to memorize their functional groups by recognizing them in structures. Compounds that contain the C double bond O. We know that an aldehyde, that's the fill in the blank word, the aldehyde contains a hydrogen directly bonded to the carbonyl carbon. So we said an aldehyde is C double bond O, and it ends with an H, so it's at the terminal end of a carbon chain. A carboxylic acid contains the OH group directly attached to the carbonyl carbon. And again, this will have to be at the terminal end of the carbon chain. If you see the carbonyl carbon attached within the group, we called it an ester. So notice this is the carbonyl carbon, the C double bond O, the carbonyl group. And now it's attached to an oxygen that's attached to more carbon. We call that an ester. You might see in the condensed structure where the C's are actually connected, COOC, and it continues from there. Or you might even see it simplified where the oxygens are bonded right next to each other, so they'll write CO2. And you have to envision that that carbon is attached to an oxygen, attached to another oxygen, and that chain then continues in its place. The amide family, amide contains an amine group directly bonded to the carbonyl carbon. So let's say, for example, we have a CH3 group, a C double bonded to an oxygen then directly attached to the nitrogen, and we now call that an amide. Amide and amines contain nitrogen. Amides are directly next to the carbon, directly attached to a double bond O. Are you ready to practice? Let's practice recognizing the functional groups. This is the top of page 19 now in our notes. What do you see?